I want to test how linear my vibration table is, and for that I'm going to do two exercises. The first is that I'm going to do a full sweep from 30 Hz to 130 Hz and record what the sensor measures for acceleration at each of the stops. That I'm going to store in an Excel file. Then I'm going to calculate what the average is of those values and also calculate which correction factor is needed at each of the frequency stops to see how I have to correct the input of my shaker so that the output is a linear vibration from 30 to 130 Hz. What you see here is the test setup for my vibration shaker. On the right side is a subwoofer that Enrico and I converted into a shaking device. It's controlled by a function generator that I'm programming via LabVIEW. On the right side you see a Raspberry Pi there, and that's also controlled via LabVIEW. It is taking samples continuously from the shaker. On the top of the shaking device you see a piezo sensor that is controlled by that Raspberry Pi and the DAQ board. I'm just going to check if I get some samples in when I turn on the function generator. This is not programmed yet, this is just a plain test. And that is working, turning the output off. And now let's go to the LabVIEW flows and try to see if I can measure the specifications of the shaking device, and then as a second step if I can compensate for it. So the first thing I'm going to do is run that shaking device from 30 Hz to 130 Hz, measure the RMS acceleration along the way and capture that in a spreadsheet. The second step will be to use those values to see if I can compensate over the frequency range for the non-linearities. First I'm going to check if I can talk to the device at all. I'm going to use one of the examples from the driver that I made. Let's see if I measure anything. Auxiliary voltage is on. I'm turning the vibrator on, and that works. So we now know that we have a functioning connection between the vibration table and LabVIEW. Let's now run the first example where I'm going to capture the full range of vibrations from 30 to 130 Hz and write that to a spreadsheet. This is very uneventful because we will see a flow stepping 1 second at a time through all the frequencies. It will set the frequency of the function generator. It will wait a second to let the mechanical parts stabilize, and then it takes a sample, writes it to Excel. Once those values are written, I'm going to take one of my support spreadsheets in Excel to calculate the correction factor at each stop. So I will paste the measurements of the run that is happening now in this column C here, and then this spreadsheet will calculate first of all the average of all those measurements, and then it will put in a correction factor that will set how much I have to correct the input signal of the shaker to get a linear output if everything works correctly. I will then put those values, the correction factors, into another spreadsheet, and that will be used as the input in my final execution. LabVIEW will read this spreadsheet, and at every frequency it will apply the correction factor that we calculated here. And if everything is fine and the stars align, I would get a linear output from the piezo sensor when doing that second run. And while that's happening, let's have a look at how the software is executed on the Raspberry Pi. The instrument has two services. One service that controls the data acquisition board, and another one that acts as a SCPI layer in between. And LabVIEW talks to both of them. It will talk to the SCPI layer to set the DAQ board's attributes. So if you want to set the sample speed or you want to start sampling, that typically happens via the SCPI layer. And the instrument layer itself LabVIEW will talk to that to a raw data port to acquire all the data, all the samples very fast over the network. The software is integrated into Linux systemd, so it runs as a service, it starts as a service, and you can also ask its behavior at any time to see if there are any errors and if both processes are still running.
And you will see that the finished indicator will light up, showing us that the flow has succeeded and has done all the steps.
Happening now, the last step will start and we're finished. The file is going to be written now and I'm opening that. It is this file here that is written at this time of the day. Opening it in LibreOffice. Because I have the Belgium regional settings, I have to replace the dots with commas to be able to calculate. We can have a pre-look on how the behavior of our device is, if it is linear or not, by making a graph. This is not necessary, this is just to give a view of what it looks like. And it is not linear at all. This is what I was expecting. A first peak at 56 Hertz and then a second peak at, it's a bit lower here than I expected, like over the around 110. So this information here that we just captured, I will copy that from this spreadsheet, paste it into the correction spreadsheet, and then see what it does. So you see here that this was the original values we sampled a minute ago. This is the correction factor that my spreadsheet calculates to be applied to the input to have linear output, and then this is the predicted linear output. I bet it's not going to happen, but I'm going to try this anyways. So I'm now going to copy all the factors here, because I'm going to put them in a spreadsheet that will be used by my flow to correct the next run.
Saving this file.
In CSV, we don't need it anymore. LabVIEW is going to use it. And now I'm going to run a second flow, the one that is called sweep with compensation. And this one has two spreadsheets. One spreadsheet that it's going to use to write the results to. And the second spreadsheet is the one that I just updated with the compensation factors. And that's each increment from 30 to 130 Hertz. It will apply that, that factor to my function generator, to the input of the shaker. Let's run this. And again, it's going to be non-eventful.
Because it will take a few minutes to run through this.
But you can see that all the factors that we entered into the spreadsheet, and we should be able to follow them here, are applied to the input of the shaker. So we're at loop 5 now, 114, that is this value here. Next one will be 110, next one will be 108, and so on. And finished. This was it. I'll now go and look at the spreadsheet that it created. I'm going to open it and check if we now have a linear outcome. And now let's do a first check and see if this yielded any results. Line graph. Smooth for your pleasure. first column as label, and I'm turning off the legend, and it definitely did not do what it was supposed to do above 100 Hertz. I told you that the device clicked into a safe mode, so that's why I do believe that once we are past 95 we cannot trust the data anymore. But let's compare. Let's see what we have here in this measurement compared to what I had in the first run. So this is the result of the exercise. It's not spectacular above 90 Hertz, but in the range of 30 to, let's say, 90, we have smoothened out the behavior of the instrument. I think that's what I have to settle for at this moment, what I practically can achieve. So this is the red one is the wild first measurement, where the input was always 500 millivolt peak to peak. The second one where I compensated, it does compensate a bit. You can see that the blue line is more linear or less non-linear than the original one, but perfect it isn't. And then again, let's forget about what happens after the 90 Hertz. I believe that part can't be properly controlled.